I like to switch over to our next presenter in the SIA webinars. So his name is Peter Phelmet. So Peter Phelmet is from the company Vector Informatik. Thank you, Peter, that we can have you here today to present us something about the impact of KNFD to J1939. So Peter Phelmet is a group leader in the tools for networks and distributed system product line and responsible as a strategic customer consultant, strategic business development for automotive Ethernet. He has been with Vector Informatik since 1995. Before that, he studied computer engineering at the University of Applied Science in Esslingen in Germany with a focus on automation technology. So Peter presents today the KNFD, a vitamin shot for SAE J1939. So Peter, please share your slides. The stage is yours. Thank you.
Okay, then yeah, thank you for the kind introduction and welcome this morning or maybe afternoon from wherever you join us here. I would like to speak today and give you an overview of the feature set of improvements of KNFD based J1939. And I call it KNFD a vitamin shot for J1939 because it really improves those capabilities. The agenda is structured in 6 points. First, I will give you an introduction with the motivation. Then I will go through the features, give you a short overview, and then we will dive into the details a little bit more. And at the end, I will walk through a live demonstration so that you can really see this is available. It works, it does make sense, and then the conclusion. And then after this, you may have a chance to ask questions by means of the Q&A section. So what is the motivation for change? Why should J1939 change anything since this is around more than 15 years and it is working, it is spread all over, it is in heavy duty vehicles, it's in forestry and construction machinery already available. But it turned out that they all have some issues, and with the improvement of electronic systems, it is getting more and more hard to design those systems. So the committee, the J1939 committee, has identified 3 major issues, and one issue is bandwidth. There's always a problem. The second issue is bandwidth, and the third issue is bandwidth as well. So it's all about bandwidth and a lack of bandwidth that we experience in the, let's say, classical J1939 based world. The demand for the bandwidth is mainly coming from the increasing complexity and the number of ECUs that are used in today's vehicles and applications. And simply by increasing this number of ECUs, the communication demand goes up, and we will experience a lot more communication. And this cannot be handled with the existing bandwidth. The other reason for using more bandwidth is the functional safety. This is a topic which is getting more and more important. And typically, functional safety simply adds additional payload or additional data bytes to your control communication. And so this has also an increase of the bandwidth as a consequence. And the third one, this is a relatively new topic. This is getting more and more important. It's even today around, but it is security, and it exactly faces the same issues than functional safety. Security simply adds bandwidth from a high level of from a high level. If you look from a high level down to the problematic. Security is really a complex topic, but at the end of the day, it simply adds additional payload with adding signatures and doing the encryption. So therefore, this extends the need for bandwidth as well. So this is all about. And so what can be the solution here if we really have to overcome the limits of the bandwidth? Possible solutions that we have discussed in the J1939 committee is that we simply need to further increase of baud rate, going from 500K to higher baud rates. But as you know, with a classic CAN, you will experience a limit at 1 megabit, and 1 megabit is really not feasible in heavy-duty industries because the length of the bus length will be shortened or limited to less than a meter, and so this is not really working. So this option is not really an option. And the other thing that we really looked at is packing the existing data more efficient. So whenever we tried this approach, we figured out that based on the existing parameter group definitions, this is not so easy. And at the end of the day, it would require a new protocol scheme. So we probably would have to switch over from the all broadcast communication scheme that we do today to a more service-oriented communication, so that we have only on the network the information available that is necessary for this particular requirement, for this particular application. And but that would require a huge change in the protocol, and then we cannot reuse, or we cannot establish somehow compatibility or no layer of the OCI layer model. And that would also cause, as I mentioned, break the backward compatibility, and that would result more in a revolution than in an evolution. And if you have takeover parts from old trucks to the latest development, that would really be hard to overcome. And so therefore, all those possible solutions suffer a little bit. And then finally, discussing this in detail, it turned out that at the end of the day, the committee really came to the conclusion that we expect that all these measures that we discussed based on existing components, so staying with classic CAN, staying with our protocols and only tweak them a little bit, will not give us the necessary increase of bandwidth in the foreseeable future. So therefore, this is considered not to be an option, and the committee goes a different way. So therefore, we really looked and put on the table what is available today, and those decisions goes back 5 years. So therefore, CAN XL, as has been mentioned in the previous talk here, is not an option, because at that point nobody talked about CAN XL, or it has not been around and is not proven. So therefore, we looked very closely to Ethernet technology and CAN FD technology. And then finally, the decision really goes to CAN FD. And I know it's not a clear decision, so there are a lot of arguments why not using Ethernet or maybe even other technologies. It was, as always, it's a kind of a compromise, and there are so many requirements and things to consider, so that finally we came to the conclusion we go with CAN FD. And we expect that this is less complexity with physical layer and protocols, especially compared to automotive Ethernet. If it comes down to a switched network, then we believe it's less complex, and maybe at the end even also less expensive. We believe by staying with CAN technology, especially CAN FD, we get a simpler migration path than if we would really go to a complete different network approach, because that would also cause probably a change in all the other ISO OC layers, because it does not make sense to switch over to Ethernet and then simply stay on the application layer with the all broadcast approach. And then we get dual use for ECUs. So the migration path, if we have takeover devices, so that we can easily integrate them, or even use new one in old networks, so that we do not have to have multiple replacement ECU on stock, so that we can use the latest development also for the old truck, because it can be switched from classic to FD and vice versa. And then, as I mentioned earlier, yeah, it's at the end of the day, we believe it is more cost efficient, but that has to be proven. And so this is more a systematic approach, and the calculation of costs on a committee level is always a little bit tricky, because it's not so easy to calculate the overall cost and with respect to the overall system design and so on. What we can probably compare is integrated circuits if they are available. So this is the assumption where the calculation is based on, but it may not really reflect a individual calculation on an OEM level. So this was everything at a glance. So where to get more information, if you really want to have it very detailed, then the good news here is I'm not talking about anything that will come in future. I'm talking today about a feature or functionality that is already available. So the committee did the work, and we finished the work by March this year. And the result has been documented in 2 new J1939 documents. So the physical layer related parts are summarized in the J1939-17 document. This has been released last December. And then this year, we have put all the communication protocols, so let's say the data link layer related stuff, into a new document that is called J1939-22. This has been released this year in March. And you can immediately, right after this session, you can go to SAE, download those, and can start reading, walk through to the document, and maybe start doing your implementation if you are that attracted from these papers. There will be other documents like the J1939-82, so which is the compliance part. This will be updated. The committee is already working on that. I have no dates when this will be released, but we are working on it. It will not take too long. And then the specification for functional safety and security is not available now. The committee is also working on this, but we will hear about safety and security in the following slides a little bit more. So then I can probably more precise my talk here. And then finally, if you are really a early follower of these activities, you may know that CIA published documents about CAN, FD, and J1939 earlier, a couple years back. And those documents, the 602-1 and 602-2, are now replaced. So CIA will withdraw these documents, and the only documents that are left over now is the document -17 and -22 coming from the SAE. So don't rely on the document 602-1 and 602-2, since they are considered to be outdated and there will be no maintenance. And so the -22 and -17 documents are now the official documents. And by the way, they have been improved. They are not identical twins to the CIA documents. Okay, then this was really at the introduction level. And then now let's have a look at the details. So J1939 FD at a glance. So the general design aspects that we set with our activities is that we would like to use the CAN FD bandwidth very efficient. So that means we use higher data rates, of course, and we would really like to utilize the complete payload capacity of a CAN FD frame, since the CAN FD offers data length up to 64 bytes and is not limited to 8 byte. And using CAN FD and limit it to an 8-byte payload field, that would probably not be the optimum that you can use CAN FD. The classic extended frame format and the classic basic frame format shall not be used on a J1939 CAN FD network. However, there's no rule without exception. For very, very specific functionality, such like address claim, which is only or mainly active at the beginning, at the startup, and the detection of the network type. So if you utilize the new FD protocol and you attach this device to a legacy J1939 network, then for this purpose, it is allowed that such a network may use these classic extended frames format for figuring out to which data link it is connected. But mainly the classic extended frame format and the classic basic frame format shall not be used anymore, because we will learn later about the technical reason behind this. So this is really a aspect that comes into the play if you're dealing a lot with proprietary messages. Then the option, this is a new option that comes along with CAN-FD and the protocol improvements. Now you have a chance to use J1939 with 29-bit CAN identifiers or 11-bit CAN identifiers. It's not a one-to-one replacement. You will also learn later on about the details here. But the advantage using 11-bit CAN IDs is simply because you can spend less time in the slow data rate, and you can shorten this data rate by means of the usage of 11-bit CAN identifiers. This will simply improve the throughput and the efficiency of the available bandwidth. But it is also okay if you stay with 29-bit. It may not be a big difference, but it is probably in the range of below 5%, maybe 2-3% of bandwidth increase that you can experience if you use 11-bit wherever it is possible. And you can only use a subset of 11-bit CAN IDs used for proprietary communication. So there is a kind of a limitation if you are used to use 11-bit CAN IDs in the past. Be careful, the new CAN-FD protocol does not allow you this. So there's a very, very strict limitation on this usage of 11-bit CAN IDs. Very good news is, and this is really a design goal, is that we can use and stay with the existing parameter groups. So on the application layer, there is no change or nearly no change. It is really very easy, and you only need to replace the lower layers in your communication stack. One consequence is that we maintain the same controller application address scheme. Today, the address scheme is limited to roughly 254 nodes. And so we did not extend this address scheme, which may lead to the situation that you still have to do dynamic network addressing even with CAN FD protocol approach. We discussed this a little bit in the committee, but at the end of the day, we said no, we don't need this, and the dynamic address assignment is already available and used, and so we can stay with this because it has no practical impact. Then the native support for functional safety and security is, so to say, built into the protocol, which is really great. And it is not built into the parameter groups as it has been before. So therefore, this gives us a variety of options and really support safety and security on a complete different level, which is great. And then last but not least, there was a requirement, most likely coming from European OEMs, but nevertheless, it is important to mention here. The new CAN-FD J1939 approach fits into the AUTOSAR communication requirements. So with other words, if you are using AUTOSAR as the way to model and create your software, then you can just by configuration use this AUTOSAR stack to do the CAN-FD. There are exceptions, so you need, I guess you need For the transport protocols, we learn later about those. You need additional modules, which needs to be supported by your AUTOSAR stack provider. But in principle, so J1939 CanFD based, and the approach we are discussing in the further slides really fits perfectly into the AUTOSAR model. And this is really this really gives you the freedom if you have AUTOSAR on your proprietary networks and you need 1 or 2 J1939 FD networks, then you can seamless move information from one network to the other network without doing too much protocol translation. Which at the end of the day will only produce hot air. So therefore, those are the general design aspects. You may keep this in mind if you think about why things are as they are. There are certainly other aspects, but those are the major ones here. Okay, then starting with the parameter group. So all parameter groups and parameter group number, including the suspect parameters and suspect parameter numbers, stay the same. So on the application level, J1939 is the same. You don't need to change anything. The parameter groups you have used the last 10 years still stay the same, and you can still use them. There's no change or no need to change anything. Due to the CanFD capabilities, it is obvious that on the transmission layer, so below the application definitions, we can use and will make use of the additional lengths. So typically, the design of today's parameter groups follow the simple rule: stay within 8 bytes. And we expect that in the near future, the more and more CanFD is supported and accepted by the industry, we will probably experience larger parameter group definitions, because you will also see this later. We don't need special overhead. So parameter groups will likely go to the range up to 60 bytes to fit into a single CanFD frame. But they are still parameter groups. As you know, on the application layer, a parameter group has no technically no size limit. It is practically limited to 8 byte because of the underlying CAN classical transmission protocol. And so here we can really experience a lot more freedom. And the other thing, excuse me. The other thing is the way of handling the assurance data. I mentioned this earlier. The assurance data is not part of the parameter group, as you can see on the left side on the picture. So the parameter group stays as it is, and then you can append the assurance data for safety and security. And this is a difference in comparison to the classic J1939 approach, where the parameter group comprises the assurance data. So if you look at today's parameter groups, you may find not at all parameter groups, but at some of them, you will find additional CRC, checksums, and whatever, and they are part of the 8 byte. And in the future, we expect this is no longer necessary. So you can stay with the existing parameter groups who have no extra CRC signals defined, and then later on you can attach them simply as an attachment to the parameter group, and it does not need to you do not need to modify the specification and the signal layout of your parameter group. So this gives you a lot of freedom, and it allows you to enable parameter groups who have not been designed with respect to safety and security. So you can simply attach assurance data to every existing parameter group, and you do not need to reserve and think about at the point in time you define the parameter group if you better have to immediately assign a assurance data or not. So this can be done afterwards, or on the system integration or system design point in time, you can make this decision and say, okay, for me, this parameter group is that important. I need the assurance data, or it's not so important in my system. We don't need them. And then you don't need to transmit them, and you will not waste the payload, the bandwidth. And all this information then goes into the payload. So this looks at the first glance here, similar to between CanFD and Classic. On the next slide, we will see there are also differences, and this is probably the major difference that you will experience is how we map the parameter groups to the CAN frame, to the CAN data frame. And all parameter groups of a controller application that you need to from a single controller application that needs to be transmitted can share a single CAN frame. In contrast to the classical J1939 approach, and if you look at the CAN-FD J1939 approach, and you can see with the green boxes, they will fit all into a single CAN frame. And if you look on the other side to the classic J1939, you will see 3 individual parameter groups, and they will finally end up in close to the data, to the CAN data frames. Then you will see that the classic J1939 is the parameter group is split up into the payload as well into the CAN identifier. So the transmission really of a parameter group has impact on the CAN ID as well as on the payload. On the CAN-FD data side, on the side where we show the CAN-FD data frame, you can see the CAN ID field and the payload field is completely separated, which gives you freedom, especially if you think once in a while you need to establish a gateway. Then it's pretty simple. You can simply grab from the payload the data, and you do not have to assemble data by means of CAN ID and payload. So everything you need is coming along with your parameter group, and it is there at one place. This might be from the implementation point of view, a little bit a advantage. If we have now a closer look to the assurance data, safety, security, or both, then as you can see, it will be added to the parameter group. It will not be added to the CAN frame. It is a part of the parameter group, and so if you have, as shown on the example here, if you have 3 parameter groups to transmit, but only parameter group C requires assurance data, then you simply add assurance data to the parameter group C, and then this will go along with the parameter group C into the payload, and so you transmit the assurance data not to the complete CAN frame. It's just assigned to this parameter group C, which later on will allow you, if easy, to move this, to extract the parameter group C together with the assurance data, and then as one package probably move this to another network, to maybe to Ethernet or to another CAN network, and this is one package. And so if you consider this from the perspective of end-to-end safety, then this layer is completely independent of the underlying communication layer, which is a great advantage in comparison to other approaches. And you may ask yourself, this is a detail, but you may ask yourself, what if the parameter group A, B, and C do not completely fill up the payload of a CAN-FD frame? Then of course, because we cannot configure the data length of a CAN-FD frame on a byte level. So then we have to fill up the overlapping or extra bytes, which we are not going to use in this transmission. We have to come with padding bytes and fill up the payload. This is probably not the most efficient way, but this is the backdraw if we fill up the CAN frames. However, on an average level, we believe this padding is not a big pain, and the overall gain in efficiency is way more and ways higher than the few data we lost, we lose with the padding. If your data is larger than 60 bytes, then yes, of course, we still need a transport protocol. And so there is a equivalent to the existing broadcast announce message transport protocol, also defined on the new CAN-FD layer. And this is, of course, optional, and it goes from everything that is larger, every payload that is larger than 60 bytes up to 15,300. If you compare it with the classical CAN, so there is a extension, so you can transfer more information. This may help especially with the DM1, with the diagnostic message 1, since they, if there is a if there are more issues on our ECU, it is likely that you have to transmit more than 1,785 bytes. And so there's a little bit of help. And a big impact or a big improvement is that we can run such a transport protocol now in parallel 4 times. So every node has a capability to support up to 4 concurrent running transport streams. Which also addresses the blocking of the available broadcast message on the classic CAN frame. So if you usually have a diagnostic message and the system is not healthy, then the diagnostic message needs to be transmitted every second. And if there is a large number of faults to report, then it more or less blocks you the only available BAM transport protocol slot. And now a controller has a capability to use up to 4 of those transmission blocks. And so this gives you freedom to not blocking either the application, the control data, or the diagnostic data. So the transport protocol is pretty much the same than in the classic approach. So here on a reduced slide, I give you an overview what is new beside the session management that you can see in the middle. There is a new frame, the last one here shown. This is the end of message status. This is not available in the classic way. This is something that is new with the FD. And this one acknowledged from the transmitter side, yes, I have sent this amount of information. So it summarizes everything, and it on an optional base, you can attach assurance data to this transport protocol. So if you have these large amount of data with 1500 bytes, then you may add here a larger portion of assurance data. And this can be done by means of this end of message status. There's also a equivalent to the existing RTS-CTS transport protocol. As you can see, we have also increased the overall amount of data you can transmit. This goes up to 16 megabyte. And also concurrent sessions are available. So a node can now perform up to 8 sessions in parallel, which gives you also freedom to do more, and you do not have to take so much care about a blocked transmission or a blocked transport protocol session. And there's also the end of message status as at the BAM. You can also have safety and security capabilities. It looks pretty much the same as the classic one, but again, we have the session handling, we have the end of message status, and then finally the end of message acknowledge, which comes from the receiver. So there's really a handshake. So this is not new for the RTS-CTS. So there we had the handshake already, but here what is really new is again the session and the assurance data handling, which is now built into the transport protocols as well. This maybe opens the room for questions about the usage of the CAN formats. I have not put any detail on a single slide, so it is a little bit reduced. So don't take this slide as a specification, always refer to the official SAE documents. But for getting the idea and understanding the general rules, I guess this is fair enough. So we have on the application level, we have the PDUs, the application PDUs, where we have most likely all the SAE defined parameter groups and the proprietary parameter groups. So everything that belongs to SAE J1939 goes into this application PDU, nothing else. Every message that you would like to transmit on such a data link, which is not J1939 related, are called non-SAE messages. And for some of them, for a variety, not everything is possible, but for a variety of them, as I list here some examples: XCP, AutoSAR network management, ISO 15765, this is diagnostic. SAE has reserved CAN identifiers so that those can be used in parallel to the CAN FD approach. So everything that has been available in the past is now also available, even so that it is now CAN FD based. And then on the bottom level, we have the CAN frames, where at the end of the day, if you would like to transmit or receive anything, then we have to map this information to those 4 types of CAN frames: classic extended, FD extended frame format, classic basic, and FD basic frame format. And so then we have in the middle, to connect those different layers, we have the data link layer, and there we have the data PDU. And similar to what we had before, is we have 2 different data PDUs. So on the left, on here, on the, I think it's your right side, you have the DPDU1. So this is considered to be a unicast transmission. Then we have the DPDU2, which is most likely considered to be a broadcast. And then we have a DPDU3. So we will, it is also broadcast. And so now you can see that all of those data link PDUs will support the multi-PG transport. So they can all make advantage of packing multiple of the application PDUs inside the payload and transfer them. And then here the DPDU1 is also capable of handling the RTS-CTS transport protocol. The DPDU2 is only capable of handling the BAM, since this is broadcast. And the DPDU3 does not support transport protocol. So this is limited to 60 bytes in total, which will probably 4 or 5 classical application PDUs with a length of 8 bytes. And then, now how to connect those to the CAN frames. So as I mentioned, all SAE related communication, which is represented by application PDUs, goes to data PDU 1 and 2. And the data PDU 1 and 2 are mapped to CAN FD extended frame format. So this means this all goes into 29 CAN identifier bits. If you are going to use 11 CAN FD 11-bit CAN identifiers, then your application PDU must be mapped to a data link PDU 3, and this data link PDU 3 will be transmitted with 11-bit CAN ID. And so you can mix the systems, so you can use both in parallel. You can use all 3 PDU types, but especially for the broadcast communication, which is the overwhelming communication scheme we have at SAE J1939. Therefore, you can mix, you can decide on your own requirements if you would like to stay for those broadcast communication with 11 or 29-bit CAN identifier. If you are going to use transport protocols, then you cannot use this by means of 11-bit CAN identifiers. There's another term called single parameter group transport. This is only for very few dedicated cases. For network management and so on. So those are exceptions, and they are also only available for DPDU1 and DPDU2. So you have to support DPDU1 and 2, and as an option, and maybe improvement, you can also support DPDU3. And then all the other non-SAE messages, they belong exclusively to the DPDU3 and will end up in 11-bit CAN identifiers. And here on the dashed line on the lower corner here, some specific frames, especially the single parameter groups, they will be used for address claiming and network detection. They are the only ones that use classic extended frame format. Otherwise, this for any other purpose, this shall not be used. And the classic basic frame format, so the also is not used at all. And you shall not use them. And the mapping from the DPDU, the data link PDU, to CAN frames, here to give you a little bit more detail. As you can see here, the DPDU1 comes along with a destination address here, briefly written as DA, and this is why this can be a unicast. And the DPDU2 has no capability for a destination address. Therefore, a DPDU2 can only be transmitted on a broadcast message. The difference here is that the parameter groups that you can transmit has a wider, greater, has more capabilities in the addressing. So there are more broadcast parameter groups available than peer-to-peer parameter groups or unicast parameter groups. So therefore, this is a limitation, but usually this comes from the standard. So by the definition of your application PDU, you define if this is a broadcast or a unicast parameter group. And then data link parameter group, data link PDU3 is in comparison from what you are used to. If you look at the classic J1939, it does not provide any priority bit. Instead of the priority bit, it now uses a application protocol identifier. And here, typically, it is encoded which application, which non-SAE application protocol is used. And this is the reason why you cannot use 11 bits anymore for your proprietary communication, because all CAN FD nodes would probably interpret this in a different way and would not follow your proprietary rules. So now let's have, in the last couple of minutes, let's have a talk about the physical layer and the migration scenario. And so the physical layer, this is pretty straightforward. I will real quick go through this here. We have a bus topology. We have a baud rate for the arbitration baud rate. It's about 500K. And then we go to 2 megabits for the higher, for the data baud rate. The cables are defined as shielded and unshielded twisted pair. The cable, it is recommended that the cable are jacketed so that the twist is maintained. And we can have a maximum of 30 nodes. And if you have an open stub, so if you do not attach a node here, then anyhow it counts as a node. And we have two different types of ECU. This is similar to the classic approach. So ECU type 2 comes probably with an internal termination resistance, and ECU type 1 has no internal termination resistance capability, and in this case you need those external terminations. And the signal improvement circuitry transceivers are recommended by the SAE. Here you can see also some length limitations So this is a overview, and if you need to design your physical layer, I really recommend to go to the SAE document. So this is just an overview to give you an idea about the capability of this physical layer. So it is limited to 40 meter at 30 nodes. This is probably important detail. So the overall length depends on the amount of nodes you are planning to attach to your network. So if you have only 2 nodes connect together, you can go at 56 meters, and the more nodes you have, the shorter the length of the network. Migration scenarios is on the vehicle level. I know this is a topic that is really open for everybody, and everybody may have probably a mixture of those ideas that I come up here right now. So I would really stay with a couple of fundamental thoughts about the migration. And basically, if you have really a legacy network as it is displayed here, it is not able, you are not able to connect those together, and everything is fine. So they have to stay really separate. So therefore, a J1939 FD node can only be attached to the FD network, and it is not allowed. Excuse me, a classic node is not allowed to be connected to a FD network, and vice versa. FD node as such, if it is not prepared in a special way, it cannot be attached to the classic CAN FD, to the classic J1939 data link. So this is for the reasons of the previous slides. This is not possible, since the FD node will simply enable the FD CAN protocol. This will cause issues here. And on the other side, as you have seen, classic extended frame format and classic basic frame format shall not be used on this data link layer. And this is very likely that this node will utilize those features. So therefore, this is not possible. So that at the end of the day, if you need to connect both worlds together, you need a gateway. So this is the classic approach, and then the gateways can forward the messages from one network to the other. Or, and this is maybe a thing you should consider if you design new nodes, or if you have to make modifications to the existing hardware of your nodes, then I call this the advanced J1939 node. Then it is possible that you come up with a setting here that is good to have capabilities for both network layers, so that this node, if it is prepared on the physical layer side, so of course you need to pick a CAN FD capable a CAN controller, as well as a transceiver chip which supports the 2 megabits. And then you can create such a node that can probably by software distinguish if it is connected to a classical or a FD data link, and it can work on both sides. And then it can also enable and disable certain protocols like the multi-PG transport or the additional transport protocol capabilities. It will probably switch off this on this side and enable it on that side. So a new node can be designed, if you do so, can be designed to fit in both worlds. So this is a pretty good migration scenario. So use a gateway for the existing ones, and then step up here with FD node. And once in a while, you can migrate from the classic, probably by improving either the hardware and software, and move them over the time to the CAN FD network. Now, to give you a short overview, I would like to switch over to a live demonstration. And we have those 3 networks. And what we can see here now is an example. Let's concentrate on those 3 lines. So this is the classic network. It is available here on CAN 2. and it represents a transport protocol. So transport protocol command, and then the data, the two data packages. So this is one transmission that is going on, and then we have a second transmission which goes in parallel on this classic network. So this is a 8-byte parameter group, and those 4 messages are now collected by the first gateway here and forwarded by means of the new CAN-FD protocol, by means of the multi-parameter group transmission to this CAN1, which represents the CAN-FD protocol. So as you can see here, this now is CAN1. It's CAN-FD based protocol. I have already implemented the multi-PG transfer mechanism. And now the interesting part is here. If we look at the new protocol, I don't want to dig into the details. So on the slide deck, you may download afterwards. This live demo is explained a little bit better, and you will see here red boxes which explains every byte here to you. But the important thing is just as a rough indication. You see, for example, the parameter group number FEB7, and you can imagine this is the FEB7. So this is here encoded, and then you can see the data length. You can assume this is something here, and then by looking at the data at the payload, so 1, 2, 3, 4, 5, 6, 7, 8, this will be reflected here in this portion of the data. So this is the transmission of one parameter group inside the multi-PG frame. So this is a single CAN-FD frame, and it now covers a complete legacy CAN frame. And then since there is a transport protocol running in parallel, as I mentioned, so this is a second transmission with a larger amount of data. Then we can here imagine the same. So we have the FEB7. This is the parameter group that is transmitted. The C is the amount of data. So this is 12 bytes of data. And then as you can see here, for the transport protocol, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and ABC data. And as you can see here, this ends up and is completely filled or is completely available in this message as well. So we have those two parameter groups now in a single multi-PG parameter group transmitted in the on the CAN-FD data layer. And here in this example, with the 0, 0, 0 and the A here or AA here, this is the padding information, because we cannot align the CAN-FD frame exactly to every individual data length. And then so this is the communication we catched here. And then the second gateway again is taking this multi-PG frame again and recreates here on a third data link the original frames again. So now we have had a look at the CAN1, and then whatever is received by the second gateway, it will be converted into a third network, CAN3. And then as you can see here, it is exactly the same. We have the transport protocol with the two data packages plus the single transmission. And here on the final network, we have the data protocol with the single message. I have more demos here, but with respect to time, I will interrupt here my live presentation. Sorry for that. And we'll go back to my slide. So this brings me to the summary here. So CAN-FD based J1939 network is available and published as SAE recommended practice. This is very important. This is nothing that will come in the future. It is there. And with the customer contacts we at Vector have, there is really a demand from the market, and we have a lot of very interesting talks with companies of all size, and they are very interested in this technology. So if you are in this business, I really recommend you to care about this and do not ignore it. There is a huge request currently going on about this technology because it solves so many issues. There is good migration scenarios with respect to the shared application layer. So we use the same parameter group, so the applications at all don't need to be re-established or reprogrammed. We have addressed the current issues with functional safety and functional security. It is not in the standard right now, but as I mentioned earlier, if you need to do this today, you may simply take what is available at AUTOSAR. You can use the AUTOSAR functional safety and security profiles and can use them if the sender and receiver uses them as well. And then J1939-22 offers 4 to 6 times more bandwidth. This is what we have measured with some prototypes. If we compare this to a 250 kilobit classical CAN, and if we use the 11-bit identifier versus 29-bit, this is roughly about a gain of 5%. So you may really seriously think about why not supporting 11-bit and not only using 29-bit. And then we have the enhanced transport protocol capabilities. This may or may not be valuable for you, but especially with the diagnostic messages and the BAM, this is considered very helpful. And then the AUTOSAR protocol aspects, this is for some companies, this is really a very, very helpful design aspect and overall design aspect, because that will help to reduce the need of protocol translation. And you can use the same tool chain and design process. It's not like you do everything and then J1939, so everything is now the same. Okay, this is all I wanted to share with you. So there are a couple of comments from the market. I'm not going to read them here. If you download the slides, feel free and read them. And as I mentioned, there are way more requests at Vector, so we can really feel a demand. Thank you.